Good afternoon, everyone. Welcome to the workshop. I'm Daniel, Chief Architect at Bitlayer. So, sorry about the mask. So I have some allergic reaction. Today, I'm going to talk about the Finality service on Bitcoin. So, first we will go through some basic concepts, and then we will see what we have on the market, and then we will have a deep dive on the one of the most popular finalization type, and lastly, I will give you a brief introduction on the engineer's working progress. So let's get started. So what is finality? From dictionary, finality is just to settle something, and after finalize it, never change. In the context of blockchain, finality, we have a consumer chain and we have a provider chain. In this context, is Bitcoin. So consumer chain has a assertion, and it submits the assertion to the Bitcoin, and it will be finalized on Bitcoin. Okay, so then what is a finality service? It's just like the cloud computing. Some service provider turn the finality to a consumable service, and maybe by providing some friendly API, the consumer chain just obtain the finality by integrating the finality service. So I think we think the finality service are useful for Bitcoin ecosystem. These are basically some use cases of the finality service. The first one is a trustless BTC bridge, because the bridge use some night clients to check the correctness of the cross-chain message. And the second one is the rollup, and the rollup want to finalize the layer 2 state on Bitcoin for finality. And the third is verifiable computing. It is fairly simple. It just finalizes the result of the off-chain computing on Bitcoin, and the people can check the result. The last one is the additional security, because finality on Bitcoin can help some POS chain to defeat the long-range attack. I think that's basically Babylon does. So what option we have on the market? I think we have basically three types of finality service. The first one is checkpointing. The concept is very simple. The consumer can just submit the checkpoints to Bitcoin. And the second one is middleware verification. Some service provider just create a network that can handle the ZK verification work and submit the verification results to Bitcoin. The third one is on-chain verification. So the assertion and the proof will be submitted on Bitcoin, and it will be directly verified on Bitcoin. The last column we have some players. The checkpoint type we have Babylon actually is the most famous one. And for the on-chain verification type, we have Starkware, on Ethereum. And also, today I will give you an instruction about the Bitlayer's OpVM. Is a Finality service on Bitcoin. Yeah. So this, let's take a closer look at the finalization by checkpointing. Basically, consumer chain, in consumer chain, we have a checkpointer that will submit the block header and the consensus proof to Bitcoin. And on Bitcoin, it actually formed a checkpointed chain. So the clients of this consumer chain can use this checkpointed chain as a trust source. So it can defeat the long-range attack if there is any fork. I will skip the middleware verification. So let's let's take a look at the on-chain verification. In this type, in consumer chain, we also have a prover. The prover will generate the STF proof for this transaction. And the prover will submit the STF proof to Bitcoin. And on Bitcoin, we have a verification gadget which will verify this proof and decide if the assertion is correct or not. We can see that we have two types of verification method. The first one is the fraud proofs, and on the left we have validity proof. Let's go through the basic workflow of these two proofs. In fraud proof, the assertion is accepted optimistically and will be finalized after a challenge window ends. That's what we call happy pass. Well, in the unhappy pass, the challenger thinks the assertion is incorrect, so it will start challenging. So here we have a challenger and a defender. They will play a game to decide if who is the winner. Last, the game loser will lose the deposit or financial incentive. For the validity proof, is pretty straightforward. It just verify the validity proof directly on-chain. So that will give immediately result of the assertion correctness. So at the moment, ZK proof is the dominant validity proof. We also have some proof like trusted hardware, like TE, right? So but we won't cover it today. The validity proof is pretty straightforward, but the fraud proof, the protocol is very complex. So we actually have a system model to describe the fraud proofs. During the setup, we just compile the STF program into some small pieces, what we call replay units. And we then search for one replay unit to replay this unit on chain to decide if the who is the game winner. Yeah. So the core of this for-proof game is just search and replay. Okay, before we go go into detail of the search and play, we first we check some Bitcoin constraints. On left, we have some programmability issues. For example, the script is stateless, and we have no flow control. We lack of some high-level primitive, just like OP block hash, and we must emulate some basic arithmetic operations. On left, we have some runtime constraints. For example, the maximum script size and the stack depth. Then we lack of the transaction introspection. So because we have these constraints, so the for-proof game on Bitcoin is even harder to design. So let's see what we have. In this diagram, we can see actually the orange line on the bottom is a possible technical path for Bitcoin. To design search and replay, we have two options to do the replay. The first one is to replay the entire STF. I think that's basically the most L1 does, right? So that's not practical for L2. Okay, the second option is we just replay a part of the STF on Bitcoin. Then we have two options. The first one is we just replay on the granularity of instruction. And then we have the segment granularity. Yeah. It's just a trade-off between search and replay. The more work we do on search, the less work we do on the replay. So last we have another optimization. We can replay we can replay the ZK verifier instead of the original STF. So the ZK verifier of the STF program is staticized. So let's make the core design similar. So let's recap. To design a game for Bitcoin, we have this four step. Here is setup. We just compile the ZK verifier of the STF into segments. And to do the search, the defender just commit to all the segment input, output, and shared values. And the challenger can specify a single replay target. And we can replay this target on-chain. And we have a result, right? We can see that both fraud proofs and validity proofs, we need ZK verifier. So for a long time, we think that ZK verification on Bitcoin is not possible. But things have changed. Because we have the latest technical breakthrough. The left one is OpVM 2. I think we just covered in Xiaopei's talk. And on the left we have the OPCat an OpCat BIP. Yes, we also covered in Xiaohui's talk. Okay. As just in previous slides, we mentioned that the core of the verification gadget, the Finality service, is this verification gadget. So how to build this verification gadget, and is very challenging task. We have a 3 stages, and at each stage we have a problem to solve. The first stage, we have to write the ZK verifier in Bitcoin script language. So we have expressiveness problem to solve. Then we have one single huge script, but it cannot be executed on Bitcoin. So how we guarantee the executability problem? The basic idea is we just compile this big script into multiple segments. So after we have multiple runnable segments, now the last stage is to link these segments to form a complete verification gadget. So let's go into detail of these stages. Step 1 is we have a ZK verifier in Rust or C++. So we need to rewrite this verifier in Bitcoin script language. Basically, we need to do lots of emulation. For example, we need to emulate the OpVM and some big integer arithmetics, and we also need to emulate hash, because the built-in hash in Bitcoin script language is provide only very limited interface. And for Snark, we have to do lots of emulation on the elliptic curve arithmetic. And for Stack, we need to emulate the Merkle proof verification. So this work cost much effort. The work is basically some algorithm, and we apply some script program tricks on these algorithms. Okay, step 2 is sorry.
Yeah, do you use Snark or Stack? I'm a little confused. Or you use both?
You mean?
Do you use Snark or Stack?
This is for Snark, and this is for Stack. Actually, in the community we have these two solutions coexist.
Oh, coexist.
Yeah. Actually, for Bitlayer, we stick to the Stack. Yeah. So the step 2 is to make this verifier script runnable, right? So we must cut the script into multiple parts, and each of which must meet the Bitcoin constraints we just mentioned. We have 2 methods. The first one is we call it a single pass scanning. It's developed by OpVM community, and Bitlayer actually developed the first version of F-Flunk chunker is actually committed by one of our engineer, Andrew. Yeah. The second one is we just do segmenting by AST splitting. Yeah, it's Bitlayer's work. The first one, single pass scanning, is pretty simple model. For this big, huge script, we just have a scanner and scan from head to tail. And during the scanning, we just track this matrix, including stack depth and screw size. When this matrix get close to the predefined threshold, we just create a new segment and clear this matrix for next round. For the splitting AST, we build an AST from the verifiable program. And we have a huge AST here. We do a DFS on this AST tree, and also we will track the metrics when the metrics get close to the threshold. We just cut from there to form two ASTs. Yeah. If this AST is within the constraints of Bitcoin, we just turn it into a Bitcoin script. So after we finish the splitting, we have lots of small ASTs, and this AST will be turned to Bitcoin scripts. Okay, after we have a bunch of small runnable Bitcoin scripts, we need to link all these segments to form a complete verification gadget. So we have two properties to clip. The first one is completeness. It's straightforward because these linked segments must be semantically equivalent with the original STF. Here, the STF means the zero verifier. The second one is the consistency, because we need to pass some values between the segments. So the values shared by the segments must be consistent. To do the linkage, we have two solutions. It's pre-OpCat and post-OpCat. Pre-OpCat, actually, this link with bit commitments is used by OpVM. The defender will use a one-time signature to commit these shared values, each bit of the shared values. And when the challenge happens, the defender must reveal all the pre-images of the shared values. And with these pre-images, the challenger can run all the segments locally and see which segment has the incorrect output. So when challenger finds this segment, it just specifies the incorrect segment to replay on chain. Okay, this link with state parsing is dependent on OpCat. Yes, with with OpCat, we have three formally missing capabilities. We can save and restore the shared segment values in a trustless way. So the second one is we can check the transaction format, not only for the current transaction, but also for the previous transaction. The last one is we can extract some transaction content from the transactions. All these three capabilities, we all depend on OpCat. So here it just look like a covenant, just Xiaopei has mentioned. Yeah. It's actually a recursive covenant. Okay, so that's basically all the building blocks of the verification gadget. So let's see how we use the verification gadget to do the verification. So basically, we have a bunch of linked segments. So we build a tab tree from the segments, and we create links between the segments to form a complete verification gadget. When the challenge happens, the challenger just specify the incorrect segment to replay it on chain. One thing to notice is we need, for the challenge to happen, we need to inverse the segment's logic. For validity proofs, is pretty straightforward. We just have each segment will be hosted in one Bitcoin transaction, and it will be executed in sequence. Okay, so that's basically the verification gadget stuff. So actually, Bitlayer is now start working on this Finality service. So next I will give you a brief introduction of Bitlayer's work in progress. I will give you the Bitlayer's OpVM is a Finality service. We can consider the OpVM as a bridge between the gas domain and the Bitcoin. And in OpVM backend, we have we will accept the guest proof and do the pre-verification. And we also have the proof allowing. It will turn the original STF proof into a Bitcoin-friendly proof. And also, it's possible to aggregate the guest proofs to further reduce the cost. Last, we have a gameplay agent to help the guest chain or consumer chain to finish the challenge game in fork proofs. And on Bitcoin, we have OpVM verification gadget. It provides two types of verification method. The first one is fraud proof by dispute resolution, and we also have validity proof by directly verify ZK proof on chain. The on-chain verification gadget will produce some finality cookie for the guest covenant to consume. By consuming this cookie, the guest covenant will know the finality result. And it's gonna basically, yeah, actually we talked before covenant communication between covenant. Yeah, I think that's what we also need some way to enable the covenant communication. Okay, that's a simple instruction of Bitlayer's OpVM. And next, let's see Bitlayer's proof system. Bitlayer, from day one, we are sticking to the stack series. Before OpCat, we have a stack variant named tap stack. Is only for proofs. And after OpCat, we have a BF stack for proofs, and we have a BF stack for validity proof. The BF means Bitcoin friendly. So the tap stack is a stack without OpCat. So how we do it? Because to verify the Merkle path, we need OpCat. But fortunately, we have a built-in Merkle tree on Bitcoin is the tap tree. So we just use this Merkle tree emulation node and to emulate this Merkle path verification. And the on the right is some initial test data. From this table, we can see that the stack family has some advantage over star. Especially in the square size. Okay. After we have OpCat, we can simplify this tap tree and remove the tap tree emulation stuff. And I think this is a basic verification gadget on the right. Also, when design OpVM, we will also providing some useful toolchain. For example, when develop the verifier use Bitcoin script, we have some script libraries, and we will also have a OpVM compiler to do the script segmenting and do the linkage. Yes, I think we can work with the community to make this toolchain better. Yeah. Yeah. Actually, OpVM is just at its early stage. So our OpVM page is online. So please check it out. And the white paper will be released maybe in next 2 weeks. Okay, that's all for today. So thank you.
So what is the status for this pre-opcode OpVM or post-opcode this verifier segmentation? What the overall status is already implemented?
Yeah. Let's go back. The type stack is already done. Yeah, we will open source it maybe in October. Yeah, and this one we have done the design, but not the code is not ready. We are now working on it. Another question? What we want to build is a service, but it can be a chain. Yeah, and it's highly possible it's a chain. Yeah, we want to make it trustless and decentralized. Yeah.
Pardon my ignorance, but can I just check your fraud and challenge period? How long is it?
Okay. Our initial estimate is about 3 to 5 days.
Sorry?
3 to 5 days.
3 to 5 days.
Yeah, yes, our initial estimate.
Okay, sure.